Okay, so at this point, you guys got the 11 over square root of 13 times square root of 29? Okay, so realize that lovely fraction there, right? 11 over square root of 13 times square root of 29 is equal to the cosine theta I start off with, correct? I'm trying to solve for what? Theta? For theta. How do we solve for theta? You take the inverse. I'm so impressed. You guys have grown leaps and bounds in figuring that out. That took a while for me to get through to you, but both classes today are like, oh yeah, you take the inverse. No big deal. Okay, so if it's cosine theta equals that fraction, in order to find theta, we're going to do cosine inverse of that fraction, which is 11 over, and it's square root of 13 times square root of 29, which if I really wanted to, I could do the math, but realize a square root times a square root, as long as they're both square roots, you can just multiply them. So it's the square root of 13 times 29. So grab your calculator, try it with me, and let's see, we're talking degrees here, aren't we? Sorry, I gotta switch pre-calc, not calc, I've gotta be in the other setting. So, okay, cosine inverse, you can't see what I'm typing though. You can do a fraction bar if you want, 11 over, and in my square root, since it's square root of 13 times square root of 29, I could just put square root of 13 times 29, and that will work. However you did it, you can't see my answer. Did you get my answer? Okay, because if you did it and you got my answer, then that means you did something right. If you're more of a not a fraction bar person, you just did 11 divided by, you could do square root of 13 times 29. Whoops. As long as you make sure they're both in that radical. You can do it like that. Okay. Find something that works for you. So 55.5 degrees. And that 55.5 degrees is your theta. That is saying that those two vectors are 55.5 degrees apart. The angle between them is that. Now, I feel like a visual is helpful. And maybe you guys don't need the visual, but I just want to show you a quick visual here of what these two vectors look like and the angle between them. So if I just do a quick sketch, one of the vectors is 2, 3, so that's going to be right 2, up 3. So a vector of 2, 3 means it's going to go through that point 2, 3. A vector of negative 2, 5. Left 2 and up 5, yes? So it's going to go something, whoops, like that. Does 55.5 degrees as the angle between them make sense? I mean, keep in mind this is just a rough sketch, but 55.5 degrees should be that distance there. And I think we can all agree it's less than 90, right? So it fits into that range of, yeah, it should be about right. So I want you to have a visual there of, okay, that's what we're finding. We're finding the distance between those two vectors, the angle between them. Questions there? Okay, let's try B then. B asks the same question, so just a little more practice, if you will. Vector U has component form 2, 1, and vector V has component form -1, -3. So again, same formula. Cosine theta equals, now, can I go ahead and jump into doing my dot product? Are you guys okay with that? Okay. So we have the component form 2, 1 and -1, -3. How's that dot product read? What'd you say?
2 times negative 1 plus 1 times negative 3.
And that's all under a square root, right? Or, no, sorry. Dot product. Nope. You're good. You're right. I'm wrong. Okay. 2 times negative 1 plus 1 times negative 3. I got distracted by noise in the hallway and closing the door.
Yeah.
I can't multitask on this one, obviously. Okay. 2 times negative 1 plus 1 times negative 3 is going to be? Negative 2 plus negative 3, which is negative 5. Okay. Denominator. Absolute value of u. Square root of? Two squared plus 1 squared. And so that's going to be the square root of? Four plus 1, or in other words, 5. Second length, or magnitude. Vector is negative 1, negative 3, so we're going to be doing the square root of negative 1 squared plus negative 3 squared. And that's going to become the square root of 10. Okay. How do I set this up to finish it? Theta equals cosine inverse. We're doing the cosine inverse of that fraction, which really is negative 5. If you want, you could say the square root of 50. I just wrote 5 times 10, so no one questions where the 50 comes from. The 13 times 29, I didn't know what that was, obviously, and so I just left it. 5 times 10, it's 50. That's easy. I could do that. Make sure you know how to use your calculators. Cosine inverse of negative 5 divided by square root of 50. Did you get my answer? And morning class was a little concerned because it was a whole number. But that's possible, guys, okay? It happens to be 135 degrees. What?
I said orthogonal. I was just reading the next word.
Oh, I'll get there in a moment. A quick visual check. And it's not that you have to do a visual check by any means, but again, I'm just trying to show you what this theta, this angle between them, looks like. So if I have vectors 2, 1, which is right 2, up 1, looks something like that. A little farther. And I have, what was my other one? Negative 1, negative 3, which is left 1, down 3. Could that 135 make sense? And keep in mind, it's going the shorter distance, right? So in this case, the distance between them, does that look like that could be 135? I can see a more than 90, less than 180 type angle there, and that's what we need to see. Okay, so again, just a little bit of visual there. Okay. Before I turn to the next page, a little bit of vocabulary. And I'll be honest, I put the word in Google this morning and asked Google for a pronunciation because I couldn't remember which way to pronounce it. So, vectors are considered orthogonal, which has almost the same meaning as perpendicular if their dot product equals 0. Every year I go back and forth. Is it orthogonal or orthogonal? Because I look at it and I want to say orthogonal, but yeah. I don't know. I see orthogonal, but Google this morning liked orthogonal. Who knows? Okay, so anyways, not about the pronunciation, but okay, so orthogonal, what does it say it mean? Has almost the same meaning as perpendicular. What's perpendicular? Okay, 90-degree angle. So that's saying vectors that are orthogonal basically meet at a right angle. And how do we show that? Dot products equal 0. Okay, if their dot product equals 0, you know that two vectors are orthogonal. Or in other words, about perpendicular. So let's look at example 4 here. If I can find example 4, there we go. Okay, example 4 asks us to prove that the vectors u of -2, 3 and v, which is -6, 4, are orthogonal. How do I prove that these two vectors are orthogonal? Yeah, and I know I said the word prove to my morning class, and there was some, oh no, like what? We're really doing that again. But it's not so much prove as just show. You're just trying to, we're not doing a proof here. You're just trying to show that these are orthogonal, which means if they are orthogonal, the dot product is going to equal 0. That's what we're trying to check, right? Does the dot product equal 0? So, how do we do the dot product? Okay. We're going to be doing first piece times first piece, so 2 times -6, plus second component times second component, 3 times 4. 2 times -6 is -12. 3 times 4 is 12. Negative plus 12. -12 plus 12 is 0. What did we just show? That they are orthogonal. Okay? That's all we had to do. Just showing that they are orthogonal. Now, a bit of visual here. You want to see a quick visual? And again, just trying to help you picture this. Because I know as a teacher, I am sometimes guilty of, here's the equation, here's how you do it. And so I'm trying to be a little bit better, but okay, 2, 3. So if I look at 2, 3, somewhere up there, right? I think my 2, 3 kind of went at an angle or curve there, but that's all right. And -6, 4. So -6, 4, somewhere up there-ish. Good thing this is a sketch, right? Does a picture make you think they're orthogonal? I can see a right angle there. Or at least a possible right angle. So there's kind of your picture as a visual that, yeah, we just showed that the vectors are orthogonal because they have a dot product of 0, and the picture just kind of confirms it. Doesn't prove it, but just kind of helps us confirm it. Okay, so here's my plan. My plan for this entire lesson is I only needed to get through example 5. Notice that's one more example, isn't it? Okay, we're not doing example 6 and 7. That's not part of what I'm teaching. I'm only going up through example 5. I'm picking and choosing what I'm teaching this week, okay? So I'm going through example 5. Now, you'll notice I have about 3-4 minutes left, and I don't feel like I could adequately get through example 5. We'd be caught in an awkward middle. So, here's what I'm going to tell you to do. I'm going to give you the homework assignment. On this homework assignment, you can do all but the last 2 problems. I have covered everything else but 25 and 26. 25 and 26 have to do with vector projections, which is what I have not talked about. So what I'm asking you to do is to, yes, go home and do the homework tonight, all but 25 and 26. I'll write the homework up here in a moment. And then tomorrow in class, I will start with teaching the vector projection, give you a little bit of time to work on 25 and 26, help you if you need to, because that's the harder part of what I was teaching. And then I plan to check the homework by the end of the period. Understood? So, in other words, I don't want to span this on to a whole nother day. To be honest, when Ross asked me this morning, are we going to get through the notes today? I held up my fingers and showed him fingers crossed, because I was hoping. And I don't know. Had we pushed a little bit, I could have maybe gotten to example 5, but we're going to go with this as is. Sound good, everybody? So page 472, 1 through 18, 23 through 26. You just don't know how to do 25 and 26 quite yet.